Hello everyone. I am a researcher at University of Science and Technology of China. Thank you for your interest. Let me introduce our CVPR 2023 paper. Edge-Aware Regional Message Passing Controller for Image Forgery Localization. Let's begin. First, we'll give you a short 1-minute preview. In this work, we propose a novel method to avoid feature coupling of the forged regions and authentic regions for image forgery localization. Called Edge-Aware Region Message Passing Controller (ERMPC). Our key insight is that graph convolutions can control the message passing between two regions by tuning the value of the adjacency matrix, leading to effective feature decoupling. And we take edge information as the main task and use it as a basis to explicitly model the inconsistency between two regions. And that's our preview. We will provide more details about our work from now on. First is the background. Nowadays, it is very easy to edit pictures through tools such as Photoshop. These forged or manipulated images pose risks in various fields, such as removing copyright watermarks and generating fake news. Although deep learning-based methods achieve remarkable progress, most of them usually suffer from severe feature coupling between the forged and authentic regions. These methods do not decouple the features between fake and real regions, which makes it difficult to accurately locate tampered regions for carefully forged images. As shown in the figure, previous methods do not decouple the features between the forged and authentic regions, making it difficult to locate the tampered regions for elaborately forged images accurately. Therefore, it is particularly important to decouple the features of forged and authentic regions. Then, we introduce our proposed method. We introduce a new two-step scheme called Edge-Aware Region Messaging Controller (ERMPC). As shown in the figure, it is the overview of our proposed ERMPC. Taking suspicious images as input, we first use two branches to process RGB and noise separately, obtaining GR and GN respectively. We use ResNet 50 pre-trained on ImageNet as backbone network. Then, the coarse features extracted from the RGB branch are converted into edges through the edge reconstruction block. Meanwhile, guided by the reconstructed edge information, the coarse features are constructed as graph structures. Finally, the RGB features after the graph convolution network are fused with the noise information by dual attention to output the predicted fake localization map. One of the keys of this framework is to construct an edge-aware dynamic graph convolution, named as Region Message Passing Controller (RMPC). The required edge information is obtained by another module of the framework. Our proposed RMPC block controls the message passing of the inner and outer regions of the edge by reconstructing the adjacency matrix of the nodes inside and outside the edge, so as to achieve the efficient disentanglement of features between the forged region and the authentic region. As shown in the equations, we first use the edge information of the two regions to generate the matrix AE. Then we follow graph attention network, we calculate the adjacency matrix AR of the feature map. Next we take the Hadamard product of two matrices to obtain the dynamic adjacency matrix AR'. This specially designed dynamic graph convolution can effectively avoid the serious feature coupling problem between the forged region and the authentic region. In order to use the proposed RMPC for image forgery localization, it is necessary to obtain the edge information between the forged and authentic regions, which is the other key of this method. Therefore, an edge reconstruction module was developed, including a context-enhanced graph and a threshold-adaptive differentiable binarization module. We specially design an adjacency matrix learner in the CEG, which encodes global information along the nodes to assemble the global semantic information. Inspired by the sigmoid function, we develop the threshold-adaptive differentiable binarization edge algorithm, which stands on the output of the CEG to provide the learnable edges. Next comes the experiments. We synthesize a large-scale dataset of forged images based on MSCOCO for pre-training. Now I will talk about the experimental results. Our model is compared with other state-of-the-art tampering localization methods under two settings. 1. Training on the synthetic dataset and evaluating on the full test datasets, and 2. Fine-tuning the pre-trained model on the training split of test datasets and evaluating on their test split. For pre-trained model, ERMPC achieves the best localization performance on most datasets, and ranks second on Columbia. Especially, ERMPC achieves 94.4% on the copy-move dataset cover, whose image forgery regions are indistinguishable from the background. For fine-tuned model, our model ERMPC achieves significant performance gains in terms of AUC and F1. Here, we show some results to demo our model's robustness. We degrade the raw manipulated images from NIST-16 using the distortion settings to analyze the robustness of ERMPC for forgery localization. ERMPC demonstrates more resistance to various distortion techniques. It is worth noting that JPEG compression is commonly performed when uploading images to social media. Our model ERMPC performs significantly better on compressed images than other methods. The visualizations here show that our model not only localizes forged regions more accurately, but also forms sharper boundaries. It benefits from the explicit modeling of inconsistencies and the full utilization of edges by our method. In order to evaluate the effectiveness of RMPC, CEG and TDB, we remove them separately from ERMPC and evaluate the forgery localization performance on CASIA and NIST-16 datasets. The table presents the quantitative outcomes. In the figure, we show the different values of parameters K in threshold adaptive differentiable binarization to verify its effect. Being smaller is inadequate for weakening message passing, while being larger will destroy the adaptive capacity of the network. It is obvious that the setting of 500 is the optimal solution. To further verify the effects of RMPC and ER, we show visualizations of the message passing controller and the edge reconstruction, respectively. The feature visualization shows that the region message passing controller helps to learn forged features and prevent false alarms. And another figure shows that our edge reconstruction module can efficiently acquire accurate edges, which helps our model perform well. In conclusion, we propose ERMPC, a novel two-step course-defined framework for image forgery localization. Using edge information to explicitly model the inconsistency between forged and authentic regions. It provides a new research strategy to solve the misjudgment problem in the field of image forgery localization. We propose an edge-aware dynamic graph, also known as RMPC, to control the message passing between forged regions and authentic regions in the feature map. We develop an edge reconstruction module containing a context-enhanced graph and a threshold adaptive differentiable binarization module to obtain the desired edge information. Extensive experimental results on several benchmarks demonstrate the effectiveness of the proposed algorithm. That's all, thanks for your listening.